Everyone. So in this lecture we will be learning the particle in a 1D box or particle in a deep square well, which is a application of Schrodinger's time independent wave equation. So let us start. So first of all, let us take a well like this. So this is a deep square well, and this is an suppose x-axis which is extending till plus infinity, and this is a negative x-axis which is extending till minus infinity, and this is x. So here it is 0, and we are considering here it is L, and the mass of the particle is equal to m. And in this particle in a 1D box, the key assumption that we are considering, that is first of all a wave function, that is, let us consider phi of x is continuous, finite, these two things, and here the potential V will be equal to 0, and here the potential V will be tending to infinity, and here also the V that is potential will be tending to infinity, which is outside the 0, less than 0 and greater than L. So in mathematical term, if we write, then we will consider V of x as equal to 0 when x is less than L and greater than 0, and infinity otherwise. So now we will write the Schrodinger's time independent wave equation. So it is like this: minus h cot square by 2m into del 2 phi of x del x2 plus V of x, that is the potential, into phi of x equal to energy times the wave function. Now if we consider for x greater than 0, x greater than L, and x less than 0, then we can see that the V is tending to infinity. So in this equation, if h square by 2m del 2 phi of x del x2 plus V of x phi of x equal to E phi of x. Now here if we see that if this term is tending to infinity, and this should be a finite number, this should be a finite quantity, this whole right side thing. So if this is finite, then the left side should also be finite, and if a part of this is tending to infinity, then it will anything with infinity will be tending to infinity, so it will be infinite and this part will be finite, so it is not possible. So therefore from this condition we get that the compulsorily wave function should be equal to 0 when the particle, or when we are considering x equal to greater than L or x equal to less than 0. So what is the meaning of this? This means that there is no particle present outside the box that we have considered. And for so we can rewrite this above equation as, let me just copy it and I'll paste it here. So we can rewrite the above equation as this part will be gone and only we will get this equation. And for the x ranging to L to 0, we will be having the potential equal to 0. So if the potential equal to 0, then in this equation we can see that if the potential is 0, then this quantity is becoming 0. So it is again becoming this part, this whole part. So here we are considering potential of x equal to 0. Therefore we will just get this equation itself. So we will just copy it. Now we have get this equation from both the conditions, so we can generalize it as this is the main equation. So now if we solve this a little bit, then we can see then that del 2 phi of x del x2 plus 2me by h cut square into phi of x, that is equal to 0. So now this is a standard differential equation, and if we consider that 2me by h cut square equal to k square for our convenience, then we will get this equation, or we can rewrite it as del 2 phi of x del x2 plus k square into phi of x equal to 0. So this is a standard differential equation. Also we have learned it in simple harmonic motion. So how we can solve it? We can just take a trial solution, that is phi of x, let us say it is equal to something like a and an arbitrary constant, and e to the power of like we can say kx. We can take this as an arbitrary constant a and then exponential of kx, because in the SHM what we used to get was del 2 x by, or let us take y by del t2 plus omega square y equal to 0. Then we used to take that y equal to a e to the power of omega t, or not omega t, or let us take omega t. We used to take alpha t. So let us also take here it as alpha. So if we take it as alpha, then we will get del 2 phi of x del x2 equal to a alpha square and then e to the power of alpha x. So if we put it in this equation, then we will get a alpha square e to the power of alpha x plus k square, and then a e power of alpha x equal to 0. So if we consider a e to the power of alpha x common, then we will get alpha square plus k square equal to 0. Now this part, if it is 0, then it is a trivial solution. So this part need to be 0. So if alpha square plus k square equal to 0, then alpha is equal to plus or minus iota k. Now put it in our equation, this in the wave equation, that is phi of x equal to a e to the power of, or let us consider this as 1 or this as 1 of iota k x, and another wave function will get, that is phi of 2, that is a2 e power of minus I k x. So to get our original wave function, we need to add this both, that is phi of 1 phi of 1x plus phi of 2x. So if we add this both, then we'll get a1 e power of iota kx plus a2 e power of minus iota kx. And we know that by the Euler's theorem that the expansion of e power iota theta equal to cos theta plus iota sin theta, and similarly e power of minus iota theta equal to cos theta minus iota sin theta. So if we apply it here, we will get phi of x equal to a1 cos kx plus iota sin kx, and put it inside the bracket, plus a2 cos kx minus iota sin kx. So if we simplify it further, then we will get a1 plus a2, or let us take a1 minus a2 into iota sin kx plus a1 plus a2 into cos kx. So now let us consider that this part as a sin kx plus b cos kx, where I have considered a and b, these are all arbitrary constants, so we do not need to care about the value of those. So we can take a numerous times, and here we will take b as I'm really sorry for this, but no, it is okay, a1 plus a2. So now we have got this function of wave function. Now we'll apply the boundary conditions. Now if we go into deeper, then we can see that the wave function need to be continuous finite. So if it is continuous, then the wave function in this area, that is x is greater than L and x is less than 0, this is 0. So if we see the limiting value from this side, that is becoming 0. So if this is continuous, then from the right side also it is 0 to be continuous. Therefore at x equal to L and x equal to 0, the wave function is equal to 0. So we'll apply the condition of x equal to phi of 0 equal to 0. Then we will get a sin 0 plus b cos 0, which becomes b. So from here we are getting b equal to 0. So if b equal to 0, then our wave function phi of x is getting reduced to a sin kx. Now if our function is this one, and if we apply our second boundary condition, that is phi of L equal to 0, we get a sin kx or kl equal to 0. So now kl, here you can see that L is not equal to 0, k cannot be equal to 0, because if k becomes 0, then our this whole function is becoming a trivial solution, so it is not equal to 0, and a is certainly not equal to 0 because it is an arbitrary constant. So therefore the sine function, that is sine of KL, should be equal to 0, which means KL should be equal to n pi. Now here what can be the value of n? N can be 0, 1, 2, 3, 4 or whatever. What can we get? So if we consider n as 0, then you can see that this whole solution, that is at n equal to 0, it is becoming 0, this one. And if we see that, this part I'm finding, just a second. So n, so what can we consider as n? So if n becomes 0, then our KL will be equal to 0, and for that case K equal to n pi by L. So if n becoming 0, then K is equal to 0. So we have earlier discussed that if K is equal to 0, then it is becoming a trivial solution, so we cannot consider n equal to 0. So our n will be positive integer, that is 1, 2, 3, 4 and so on. And why we are not considering negative integer, that is minus 1, minus 2, minus 3, minus 4, is because if we consider as minus, then what is changing? Only the sign here, negative, is coming. So it is also an arbitrary constant, we know, a, so it will compensate it, so there will be no change in the wave function as such. So that's why we are not considering that negative numbers, and we are only considering the positive integers. So now if K is equal to n pi by L, then our wave function becomes phi of x equal to a sine n pi by L x. Now here we can see that a is an arbitrary constant and we do not know the value of a. So one more condition we forgot to write here. It is a square integrable function. Square integrable function. The wave function is a square integrable function. So if we normalize, so we will get this a will change in accordance to the x. So let us take, or n. So let us take this as phi of n and s of n, and this is n. So for every n, the wave function will change. So let us take that integration minus infinity to infinity. We are getting that probability of finding a particle, that is phi star of sub n x into phi of x of n dx should be equal to 1. Or let us write it as, this can be broken down into minus infinity to 0, that is phi star sub n of x into phi n of x dx plus 0 to L phi n star x phi n x dx plus again from L to infinity phi n star x phi of x and dx. So we can write this part, left part, is equal to this part. So from here we can see that the wave function is 0 outside the box. So here v is tending to infinity and phi is equal to 0. Here also phi is equal to 0. So till minus infinity to 0, this wave function, there is no probability of finding the particle over here. So it is becoming 0 and it is becoming 0. And all the probability of finding the particle is inside the box. So 0 to L if we see, so if we consider only this part dx, so it will be 1 because the maximum probability which is 1 and which is the probability of finding the particle, it is inside the box. So now let us see the wave function, that is an. So we will take a of sub n whole square, integration of 0 to L, and then it will come sine square n pi by L x dx equal to 1. Now we know that sine square x equal to 1 minus cos 2x by 2. So by applying this simple trigonometric identity, we will get an mod square by 2 integration of 0 to L 1 minus cos 2n pi by L x and then dx equal to 1. So an by 2 and it is modulo square. So if we are seeing the integration, so it becomes x minus of L by 2n pi into sine of 2n pi by L x from 0 to L equal to 1. Just let me check that if I have done everything correct or not. Yes, it seems correct. So now if we apply the limit, so it is becoming L minus 0. If we put into sine function, then it is becoming 0, and then minus of, I am really sorry, if you are putting L in this whole function, then first of all this is becoming L, and if x is equal to L, then L and L get cancel out, and after cancel out it becomes sine 2n pi. So 2n pi is 0, and minus of this 0, if you put it in x, then it is 0, and minus of sine of 0 is 0 equal to 1. So we are getting a of n mod square equal to 2 by L, which implies that an equal to square root of 2 by L. So now we have got the value of our arbitrary constant, so we can write it as that a of phi of x, that is suffix n, equal to square root of 2 by L sine of n pi by L x, and this is an eigen equation or eigen function, and for every eigen function we will get an eigen value. So how we will get it? Let us see how we will get it. We have taken k square is equal to 2me by h cut square, and also k square is equal to this one, and from here k equal to n pi by L. So k square becomes n square pi square by L square. So we are writing it for every n. So let us consider E sub n. That is for n we are getting an eigen function, value. That is coming E of n equal to n square pi square h cut square by 2m E L square. So now, as we have discussed earlier, that the possible minimum value for n is 1, not 0. So if we make a corresponding table of n, and then we are making it for phi of n of x and E of n, then we will be getting something like this. For n equal to 1, we will be getting phi of n as square root of 2 by L sine of pi x by L, and the corresponding eigenvalue, that is the minimum energy, that will be pi square h cut square by 2m E L square. Sorry, the E will be not here. By mistake I have written it. So let me just rub it off. 2m L, then L square. Yes. So this is the minimum lowest possible energy. Similarly, for n equal to 2, we will get 2 by L sine 2 pi by L into x, and here we will get 4 pi square h cut square by 2m L square. And if you consider one more, we will get root 2 by L sine of 3 pi by L x, and then we will get 9 pi square h cut square by 2m L square. So these are all quantized energy. You can see that this is depending on n square, so that n is quantized. And if we draw the corresponding wave function or eigenfunction graph, then we can see that if we consider this is n equal to 1, and let us say that this is L equal to 0, let that extend it furthermore, and let us take that this is L equal to, let us take this is x, yes, and this is x equal to 0, this is L by 3. We will take this as L equal to x equal to L by 2, and this as, let us say this as x equal to L by 6, or rather this is L by 6, or this is L by 3. Now this is where we are considering it as L. So this is L and this is extending like this. This is L by 2, and we will draw it for 3 separate n, that is n equal to 1, n equal to 2, and for one more, that is n equal to 3. So for n equal to 1, we can see that this function is becoming 0 at x equal to 0 and also at x equal to L, and between this function is not becoming 0. So from 0 to L this graph will somewhat like this. And if we see the second one, in the second one we can see that first of all the x becomes 0, then this function this one becomes 0, and also at L by 2 it becomes 0 because then it will be sin pi, and sin pi is 0, and also at L equal to x equal to L it becomes sin 2 pi, it is also 0. So we are getting at x equal to 0, x equal to L by 2 and x equal to L zeros. So our graph will be somewhat like this, a sine curve. And for the third function, if we see that where it is becoming 0, at first x equal to 0 is a 0 condition, x equal to L is a 0 condition, also x equal to L by 6, or this is L by 3 and this is 2L by 3. So at L by 3 it is becoming sin pi, so it is 0, and also at 2L by 3 it is becoming sin 2 pi, so it is also 0. So we will get a graph somewhat like this. Here we'll get a maxima, and here we'll get a maxima, and here we'll get a maxima, like this. So these are the graphs which are corresponding to the eigenfunction, and we have considered n equal to 1, 2 and 3. Now why if we deep dive into this eigenvalue, that is energy, so this is representing as the inside the potential well, the potential energy is 0, therefore this is representing the kinetic energy. And we are finding one more reason that why n cannot be equal to 0. So if n becomes 0, then E of n, that is E of 0, becomes 0. So what happens when the E of 0 becomes 0? So if the E of 0 becomes 0 and V is also 0, then total energy becomes 0. And if energy becomes 0, then there will be no momentum. Momentum also becomes 0. And if we can say with 100% certainty that the momentum is 0, then it will be 100% uncertain to find the position of the particle due to the Heisenberg's uncertainty principle. So the particle will be like in x from 0 to infinity, we can say particle x belongs to from 0 to infinity. But we know that the particle is inside the box, so it should be between 0 and L. So it is contradicting our assumption that the particle is inside the box. So that's why n cannot be equal to 0. So this is the whole summary, and hope everyone have understood. Let us just recapitulate once. So we have considered a particle in a 1D box of mass m, and where the potential is 0 and phi is the wave function, that is 0 outside the box, that is there is no probability of finding the particle outside the box, that is we are considering the ball inside the box, and the potential outside the box is infinity, here also infinity. And we have considered the key assumption, that is not assumption, that is the wave function is continuous, finite, and a square integrable function. So now why is this square integrable function? The square integrable function is because we need to normalize that. And this v of x, if we write it is and in mathematical term, then it will be 0 for x between 0 and L, and infinity otherwise. And this is Schrodinger's time independent wave equation. This is minus h cut square by 2m del 2 phi x del x2, and this one. So we have taken for x is greater than L and x is less than 0. We are seeing that the v is becoming infinity, so this for this whole term to be finite, phi of x should be compulsorily equal to 0. So from this we are getting this condition, that is phi is equal to 0 outside the box. And for the x ranging from 0 to L, v of x we have seen that it is equal to 0, so it is again becoming this same quantity. So we can generalize it as this term for the both the cases. So now this is a differential equation. Now we have rewrote it like this: del 2 phi x del x2 plus 2m e by h cut square into phi x equal to 0. And now we have considered k square equal to 2m e by h cut square, and now this becomes like this, and we have taken a trial solution, and we have arrived this result. Now we have got two wave functions, this one and this one. Now to get our original wave function we need to add both this, and after adding both of this we are getting this term. So we have considered iota into a1 minus a2 as a and b equal to a1 plus a2. These are all arbitrary constants, so we need not to worry about the value of those. And if we consider the boundary condition, that is it cannot be discontinuous, the wave function, as it is here continuous, so the limiting value from both the sides should be equal. So if the limiting value from the right side is of phi is 0, then from inside also it should be equal to 0. So therefore phi of 0 is equal to 0, and we are getting b equal to 0. And if we apply the second boundary condition, that is phi of L equal to 0, then we are getting a sine KL, and for this we are getting sine KL equal to 0, as KL cannot be equal to k cannot be equal to 0, and a is also not equal to 0, then because then it will be a trivial solution. So here also n is not equal to 0, because as we have said that due to Heisenberg's uncertainty principle, and also that k cannot be equal to 0 because it is becoming a trivial solution. Therefore we have taken phi of n of x equal to an, and sine n pi by lx. For every n it will be corresponding to a new wave function. So if we are finding the probability, so from minus infinity to infinity we will get definitely the probability as 1. So how we are getting, we have rewrote this as minus infinity to 0, and this is becoming 0 because this term, because the probability of finding the particle outside the box is 0, and from 0 to L it is there, and it is 1 because the highest probability is also there itself, and also from L to infinity is 0. So after simplifying this like this and integration, we got that a of n square equal to 2 by L, and correspondingly a of n equal to square root of 2 by L. So if we rewrite our eigenfunction, then it is coming phi of n of x equal to square root of 2 by L sine n pi x by L, and the corresponding eigenvalue, that is energy, E of n equal to n square pi square h cut square by 2m L square. And now if we draw the table, then for n equal to 1 we are getting this one eigenfunction and the eigenvalue this one, and for 2 this one and this one, and for 3 similarly this one and this one. Now to convert it into a graph, this eigenfunctions we have taken from x equal to 0 to x equal to L, and we are getting the similar like this graph where it is becoming 0 and the sine function we know. And at last we discussed about that why n cannot be equal to 0 due to the Heisenberg's uncertainty principle. So thank you for watching this lecture. Hope you understood.